been a while since we designed a new weapon or a new weapon system in a while. The last time was kind of a joke. This right here is what we built, a new suppressor system based on 1990s movie technology, and it is inferior in almost every way to actual modern real suppressors that you can buy right now. Now, because we're talking about suppressors quite a bit these days, with changes in legislation, new opportunities, we're going to invent the quietest weapon platform ever. We're going to base it on old ideas, because that is what we like to do here at T-Rex Labs. We're going to add new materials and manufacturing techniques to see how much things can be improved. I want to start off this video by pointing out that modern suppressors are really good, and they're only getting better. And as much as we can remove artificial limitations, say regulatory or legislative or taxation limits, so that the free market can actually be involved in the development of new suppressor and silencer technology, those are the same by the way, the better. There's lots of room for improvement. There's lots of room to experiment with new technologies once some of those hurdles are out of the way. And as we've talked about in the past, there are legislative moves that are in the right direction. We'll kind of talk about that some more in the video. But what if we wanted to not go with essentially the best solution? This right here is fantastic because it is an off-the-shelf part that works with regular off-the-shelf and readily available firearms that shoot off-the-shelf and readily available ammunition. This is a fantastic weapons platform. But what if instead of practicality, of just basic use, we wanted to emphasize quietness? We wanted the quietest possible weapon. Well, we're not the first people who have wanted this. Let's talk a little bit about the history of piston ammunition, or captive piston ammo. The Russians really started this. The Russians were interested in suppressed ammo for a number of reasons, which had to do with, let's just say, statecraft. Mostly assassinations, but statecraft. And in their desire for a very subtle and quiet statecraft, they worked on quiet and subtle weapons. And one of those that is really fascinating to read about is the Nagant revolver, which was acquired by the Russian army in the 1895 time period. But over time, it became a pretty popular suppressed weapon, which is interesting. Revolvers do not suppress well. There is a very large cylinder gap between where the ammunition feeds out and the barrel. All of those escaping gases are what make an awful lot of noise. But the Nagant revolver had a way to seal that right before you fired the shot, making it very interesting to suppress. And Russian and Soviet suppressed weapons are very interesting to study as you look kind of at the progression of those that move along. Next on the Soviet development timeline is probably the Makarov PB. It is a very effective, integrally suppressed Makarov pistol, surprisingly quiet at 127 dB. And generally speaking, it's got very simple baffles and metal mesh on the inside. But certain Soviet engineers wanted to go even quieter, and they developed captive piston ammunition. Instead of letting the suppressor capture all of the explosion that propels the projectile, they decided that they wanted to keep that inside the cartridge. The explosion drove a piston forward that pushed the projectile out, and all of the fiery gases were contained completely inside. The best version of this is probably the SP4 cartridge. There's a couple of different versions and experiments along the way, but that works in a couple of different pistols. And probably the most interesting of these is a revolver, the OTS-38. But there was also a semi-automatic pistol that fired this particular cartridge, and there's some contention over how good this really was, how effectively it was used in statecraft, and how quiet it actually was. We're talking about a round that is based on 7.62, and it is 43 millimeters long. So it's a pretty small space containing a pretty small amount of propellant, a fairly large piston, and then a relatively small projectile. But it is very quiet. Some people are talking about this captive piston ammunition being somewhere between 90, which is an incredibly optimistic dB rating, and 110. But even 110 is really, really good. Some of our best suppressed 22 caliber pistols are around 120-ish decibels. So being considerably quieter than that while firing a bigger and heavier bullet is pretty interesting. So I would argue that it is time for us to begin tinkering a little bit with this technology. Now, there are a number of downsides to this technology as well. Containing all of that explosion inside of a small space and not letting it escape into the outside air is kind of an issue from a safety perspective. And then there's a legislative or paperwork hurdle as well. Every single one of these magical suppressed captive piston rounds is technically a suppressor, so it needs its own tax stamp. Until January 1st, it's going to require its own $200 tax stamp fee, and it's going to require being part of the NFA registration database. So that has obviously hindered its adoption a little bit here in the States. But as we discuss getting rid of the NFA, and as we have some different strategies to do that, let's develop our own captive piston ammunition. Now, before we get started on this design, let's give ourselves a design constraint. We want this to be a practical firearm, unlike the last experiment, which means we want this to have some energy behind it, not just 22 sound levels and 22 energy. We want something that hits with a little bit more punch, a little bit more stopping power. So this right here is, of course, classic 1911. And when a lot of this weapon development was happening in the early 20th century, 45 ACP was generally a 230 grain bullet. And out of a 5-inch barrel, like we have right here, we would expect to get something like 340 foot-pounds of energy, which requires 18 to 20,000 peak PSI here at the chamber. We're going to try to figure out how to captive piston launch a projectile that's going to have similar or greater muzzle energy to 45 ACP. Which means we're going to have to get rid of another design constraint. We don't want to build this inside of a pre-existing brass package, the way that the Soviets were doing with 7.62 brass. We're going to allow ourselves to think a little bigger. I'm going to try to find something that is very much like a 12 gauge size, and we're going to operate inside of this envelope. And then maybe if we have to fudge the numbers just a hair, there is, of course, always 10 gauge. So we're going to build a new piece of brass that operates inside of roughly that space, and we're going to try to push a very large projectile, subsonic speeds, because we want quiet, and we're going to try to hit like a ton of bricks. I'm going to load an animation of this projectile firing right here. As we have the striker being fired and the projectile igniting, we're going to push along the projectile using this particular piston. Now, it doesn't look like a hydraulic piston, it looks a little bit more like shotgun wadding. And this is the first piece of new material that we're going to add. I think that we can make this thing out of Delrin. Delrin is a fantastic plastic, which is self-lubricating. That means it's very slippery. We should be able to drive it along the brass cartridge casing without losing too much energy to friction. Also, we don't want to generate too much extra heat because the propellant is going to do that for us. And then our bullet is very long and thin. So even before it fully exits the cartridge, it's going to engage the rifling. And then I have progressive rifling here. So it starts out rotating very slowly, and then it accelerates faster and faster. Now, when the bullet completely exits the cartridge, our piston becomes the plug for the pressure. As you can see, the cartridge has been necked down, not in an angled way like you normally get with rifle cartridges, but in a curve that will slowly, gradually, over a very long period of time, maybe, nanoseconds or fractions of nanoseconds, come to a stop and contain that pressure inside while the bullet continues on its merry way. Now, if you look at what we've actually built here to simulate this, we're looking at a very long cartridge and we're looking at a very short barrel, which brings us to the weapon design. This suggests to me something like, and I know you're already thinking about it, a Nerf gun. Now, nothing against Nerf guns, but I wanted something that was going to operate like this, but maybe look just a little bit better, and so this is what I have built. This right here is our revolver. Now, it copies a lot of different design constraints from pre-existing revolvers. We're shooting from the bottom of the cylinder, like the Chiappa Rhino, but also like a lot of other revolvers. That Soviet OTS-38 also fired from the bottom of the cylinder, and the top of the cylinder, that fake barrel, was actually a laser sight. Very advanced when you think about it. Now, I have tried to make revolvers fit into some kind of cyberpunk future, the way that other weapon designers in Hollywood has, and they just don't really work. There's just not a lot of reason to modernize a revolver because semi-automatic firearm operation is just superior in almost every way. The only place that revolvers really fit today, apart from the fact that they are fun, is that they work really well for shooting really big magnum cartridges when there's just a huge amount of energy, too much to run in a modern semi-auto that has regular recoil or gas operation. And we are planning on shooting a relatively large cartridge out of these things, but remember, this is not going to be a super powerful magnum hard-hitting gun. This is trying to mimic .45 in as many ways as we can. But we also want it to be super quiet, and that is where the revolver comes in kind of handy. We want as little noise as possible. This is a mechanical operation that can be fully contained in a hammerless design and muffled with some more Delrin inside so that we have all of our self-lubricating parts back here. That's going to keep it quiet. The other thing is, of course, we'll capture as much of the sound as possible inside of that ammunition. We're also capturing all of the gases. There should be no chemical residue left over when we fire this thing, and we're not ejecting any shells anywhere. The shells are going to stay inside of this cylinder, which ideally we make out of stainless steel. Stainless steel is not only a good metal for corrosion resistance, but it also is a pretty good thermal insulator. So we will fire 6 shots out of this particular cylinder. All of that heat is going to be kept inside of those cartridges. All of those cartridges are going to be kept inside of this cylinder. They're going to be safely contained, and we can put that away. It's not going to be nearly as hot as modern suppressors get when you mag dump. It's going to slowly leak that heat into this the cylinder as we hide it away. It's going to have a very low sound, chemical, and thermal signature, which comes in kind of handy when you're doing, well, I don't know, maybe statecraft. But there's other advantages to this technology as well. This is potentially the first intrinsically safe firearm ever designed. There's a bunch of electronics that are designed to be intrinsically safe because they're going to be used in hazardous environments, radios especially. If you're working on a gas pipeline, you want to make sure that your radio doesn't have any sparking components, doesn't have any unshielded electronics, isn't accidentally going to trigger a gigantic fireball. And this is kind of the same. You could use this inside of a closed environment in a way that other firearms are a little bit too risky and too dangerous. If you load this with non-sparking ammunition or frangible ammunition, maybe this is a good thing for air marshals and people inside of very fragile situations to run. Also, if it's quiet enough, maybe vets or first responders should have some of these for other things. Now, I will admit that I got a little carried away and made it look extremely cyberpunk, but you don't have to copy this exact graphical design. You could make this a bunch of different other ways. In fact, my first design was going to be all laser cut out of steel, incredibly cheap to put together. The ammo will be expensive, the firearm could be extremely cheap, and used off-the-shelf AR-15 hand grips, and it looked kind of like the Liberator pistol, that really early 3D printed gun. I decided I wanted to not look like that and not look too Nerf, so it's about 85% Blade Runner right now. But there's a couple of other features here that we will look at. This gun looks fancy and futuristic, but it is extremely simple in its operation. Because this thing is going to fire these special pressure-maintaining, pressure-retaining cartridges, there should be a lot fewer forces on the actual operation of the weapon itself. There's going to be a lot of recoil. We'll cover that in a minute. But this is a relatively straightforward design. I don't even have a top strap on the revolver here, so if you pull this forward, then you have unlocked the mechanism. Then all you need to do is just rotate this brake barrel action. I kind of want to bring brake barrel action pistols back. I kind of miss that as a mechanism. And then here you have your cylinder. Very simple, very straightforward, rotates just like it should, and then it's a very simple matter to pull the brass out and reload it. You can even carry additional cylinders. If you are trying to mitigate your thermal signature, maybe you just want to keep this giant stainless steel heatsink in your pocket cooling down and load a brand new heatsink with 6 shells in it, as opposed to continuing to operate with this one. There's some new considerations if you're looking for slightly different performances from these different weapons. Of course, we can also just, pull the stuff out and put new shells in. I easily could have cut this thing to accommodate moon clips, but this is a very crude model, like all of my weapon mock-ups. There's a very simple spring-loaded mechanism here. Once you put the cylinder back on and close this back down, this thing would automatically reset and you'd be good for your next 6 shots. Now this thing has some features that look cool, but they are a test of your revolver familiarity. So for example, we have no rear sights on this thing. We just look down this particular groove right here at the front sight. And that looks like something that is very cool and clever. It's also dual use. This groove right here is how we lock the cylinder into place, make sure that it is fully aligned with the barrel. The problem is that as you pull the trigger, the cylinder is rotating, so you don't actually have anything to line up until you're, right at the wall right before you fire. But if you don't know how revolvers work, then yeah, this is a very cool cyberpunk looking thing. The other thing that we can easily do is attach some lights and laser to this thing. One of the cool things that the Soviets had was integrated lights and lasers in their OTS-38. Remember, this is a revolver, so there's nothing going on in this grip. There is plenty of room for us to stick a battery in here and power a bunch of different little electronics that we might want to use for targeting. Now this is probably a pretty good application for a targeting laser, because this is a very short range weapon, and lasers are pretty good for seeing really short range operations. They're not so good at long range, but this thing is not gonna go very far. But now we should go back to the actual round itself and figure out how capable this thing is. Anybody can make a 3D model of something that doesn't work in real life. We want to figure out if we can actually do the job that we gave ourselves. Come up with something that can hit relatively hard as actual service pistols used to, not sacrifice actual power in the pursuit of quietness. And so we're going to have to do some math. If you go down and you look at our bullet down here, we run into some issues when we have a bullet that is set up like this. The first thing that we're going to run into is we want it to be long enough that it can be pushed by the piston, by this wadding, by this buffer here, all the way through the rifling of the barrel and all the way out. That means that it's got to be long, and it can't just be a skinny stick. We actually want it to have some weight to it. The problem is it starts to get a little bit too much weight. I started out designing this thing around a 38 barrel. The problem with that is a 38 caliber bullet that is 3 inches long, made of lead, is 1,000 grains, which is very heavy, way too heavy to impart any spin to with a little 3-inch barrel. We could make it out of copper. Copper is actually a great material for this application because it is a non-sparking metal, and it would let us do a whole bunch of different things in the future with some machining. But that is still going to be about 800 grains. So let's go down from 38 calibers to 30 calibers. It's also going to kind of make our math a little bit easier. Now we're talking about a projectile that is 500 grains if we make it out of copper and we don't machine anything away, which I'm going to get to. Now we're talking about something that is actually doable. A 500 grain projectile is a little more than twice what 45 ACP shoots. And I'm really curious to see if this is something that we can actually drive with, well, not too much space. The 1911 here, firing that 230 grain projectile, has about 18,000 to 20,000 peak pressure, but then over the course of 5 inches of travel down that barrel, that expands to where it's more like 15 to 1600 psi average. So we're trying to push something considerably heavier, let's just say twice the weight, in just a little bit more than half the distance. Now, the cool part is we're talking about barrel travel of about 3 inches, but what we're actually talking about is gas expansion that's happening back here over about 3 inches. What kind of PSI do we need inside of this chamber to actually get that done? The bad news is, if we had to push this thing down this 3-inch barrel at 30 calibers and we had 500 grains of weight, we would require a peak pressure of almost 45,000 PSI, which is crazy. The good news is that our expansion area, our expansion chamber right here, is not 30 calibers. I originally modeled this at 58 calibers because I had some ballistic tables for 58 caliber rifles. But let's just make the math easier. If this is 0.6 inches in diameter and we're driving this 0.6 inch piston down this 3-inch expansion chamber, we only need 12,000 average PSI in the entire thing. Now that still sounds like a lot. The SP4 ammo that we were talking about earlier contained much less pressure. When it was absolutely finished firing, the contained pressure inside was about 8,000 PSI, and we want some more than that here. But on the other hand, that's not a crazy amount of power. The small CO2 cartridges that you use for pellet guns, that pressure varies based on temperature, but it's 100 degrees outside, which means that that's 12,000 PSI inside of those. And they managed to maintain that with a wall thickness of 0.03 to 0.05 inches. So containing approximately 12,000 PSI inside of this particular cartridge is extremely doable, especially because we're doing it inside of this larger, sturdier stainless steel cylinder. There's a whole lot of math in our favor right here. You're probably familiar with the concept of discarding or disposable sabots that allow you to shoot a very small projectile out of a very large smoothbore barrel, usually from a tank. That gives you this very large expansion chamber at the back, even though you're pushing something much smaller with greater penetrative capability down the barrel. This is exactly the same principle, but this is not exactly a discarding sabot. This is a retained sabot, and it becomes the plug that holds in the pressure. So I think that this thing is worth tinkering with. Let's go back to our pistol and let's see what we've got. Even though revolvers are inferior to semi-autos in a lot of different ways, this cylinder is probably a pretty cool idea for us to tinker with this. The cylinder gap is actually going to help us quite a bit. If there is some kind of failure somewhere along the ignition process, I have weakened the cylinder at the front away from the shooter to direct all of that force away. And then this cylinder gap, which is usually a huge problem when you want to, I don't know, suppress a revolver or hold your fingers forward the way that you think would be comfortable. This is actually going to work in our favor. Not only if there are failures, a lot of that pressure is going to be directed out and around, and I even put a few little cutouts there to help kind of guide that. There is going to be a little bit of air trapped inside of our pressure chamber because our bullet has a much smaller diameter. I'm actually pretty confident of this thing's capability. Remember, we wanted performance that was similar to 45 ACP out of a 1911. And if this is a 500 grain projectile and we manage to maintain 12,000 PSI along here and we accelerate that thing to 600 feet per second, we actually hit a muzzle energy of 400 foot-pounds of energy. That's more than the 340 that I would expect with period ammunition out of this thing. So we are above our energy constraint. The only question now is the accuracy of this thing as it performs in the air. That's where the strength of my math fails. It is this day. I failed the kind of math that lets me figure out how to stabilize this projectile because things get really complicated once the ratio of length to width changes. We are familiar with regular ballistics that tells us that a projectile like this that has been spin stabilized by rifling is going to be the best performer. But once this thing is longer than it is wide, and at 30 calibers and 3 inches long, that's like 10 times longer than it is wide, rifled stabilization is not going to be enough. We're going to want some fins on the back. We're going to want to have some fin stabilized aerodynamics so that this thing actually lands on target pointing in the correct direction. But even that kind of depends a little bit on what it is that we're shooting and at what ranges. The fins are not going to really grab the air and direct and stabilize that projectile until it's, several feet or meters away from the end of the barrel, whereas the barrel itself can introduce enough spin that it is relatively stable as it leaves the barrel and then deteriorates as aerodynamics come in. So we probably need a hybrid projectile like the one that I am putting on the screen right now. Now, you might be asking yourself at this point, how expensive is this fancy projectile? Because it has to be milled out of copper, and then it's going to be put into this rather expensive cartridge here that needs pretty thick walls and either a custom cast or custom milled Delrin piston. We're talking about a round that costs anywhere from $1 to $10. So obviously this is a very specialty round for very specialty applications. But I do think that it's worth tinkering with this. And anybody who's better at that aerodynamic math than I am, let me know what it is that we actually need to come up with to turn this thing into a reality. And remember that at some point, the strength of math fails everybody, and you just gotta test the thing. So maybe it's time for people to start tinkering with this. Like I said, there are a few actual practical applications. There are a few different ways in which this could be used by first responders, by air marshals, by people in really difficult environments or scenarios, security guards on pipelines, things like that. If I were a veterinarian, I would prefer to have this in my truck, not instead of this, but in addition to it for certain things. And of course, it could be made to look cool, and I'll bet it's pretty fun to shoot. But the most practical application of all might be when it comes to that NFA registry. If I were to build something like this, I would probably want 200-300 rounds on hand, maybe 1,000. That is 1,000 E-forms that has to be filed. That is 10,000 fingerprints that need to be added to the database. Depending on how you look at the NFA registration, I am either causing significant problems for other Americans who are trying to get their suppressors, or I am demonstrating the failure of the system to continue to do an unconstitutional thing. That might be the most practical application that this thing has. So not only does this long cylinder, short barrel configuration look like a Nerf gun, it also looks like something that the slingshot channel has been developing. Jörg Sprave, my favorite German slingshot inventor, has also invented something like this, but it is powered by CO2 cartridges and it fires those little blowgun darts. Let him show you its features.
The 6-needler is an inexpensive CO2 revolver. Actually, it's more like a pepper box. And it does shoot blowgun darts instead of pellets or bullets. Boah. Whoa.
Now, because all of that expanding CO2 escapes, it's probably louder than a properly built version of this would be. But that doesn't stop it from being terrifying to the German authorities. The 6-needler, as it is called, is so terrifying to German lawmakers that they're already trying to change the already draconian airgun laws that Germany has to outlaw the 6-needler. And they've written the law either on purpose or accidentally in such a way that it's going to outlaw basically all air guns and CO2 weapons. And I've tried to get a little bit more information about this. I don't read German particularly well, but as Ryan pointed out, it's a very sad day when German lawmakers don't understand engineering well, or weaponry, self-defense, and the intrinsic rights of man.